Okay, welcome everybody to this talk on the orogenic peridotites of Norway. We'll have a look at some of the aspects of these peridotites and importantly see what we can learn about their study. We've got here it's a 15 centimeter lump of rock. It records at least 8 separate metamorphic events and it's got a pretty impressive history. Goes back about 3.5 GA ago, way back into the Archean. So that's what we're going to be talking about mainly for the next 40 or so minutes. If you want to ask questions, just hang on to them until we get to the end, and there'll be some opportunity to do that at the end. Okay, the Western Gneiss region. We'll have a look at that, see what it's all about, introduction of that. I'll say something briefly about peridotites and how we classify them and whereabouts we find these. And we'll go into a look at these peridotites in Norway with two very important questions in our mind. Firstly, how on earth do they get there? And then, well, so what? You know, can we learn anything about looking at these peridotites? So let's go to the Western Gneiss region. This is a view of the Gneisses out on the western coast of Norway. That's where the Western Gneisses outcrop, or they occur in this area here. There's Bergen there, Oslo there, and Trondheim up there. So it's all along this western coast. We've got quite large exposures of these Gneisses. And what are these Gneisses? Well, they form part of the Fennoscandian cratonic shield. And this is the Paleoproterozoic basement of the ancient continent of Baltica. It's the crystalline basement of Baltica. And when we look at their metamorphic ages, they range between around 1800 to 1000 MA. There's a whole range of ages between that time span. And we've also got a cluster of ages around 900 MA. And within these Gneisses, we can record 3 major magmatic events. And these events we can date, obviously, and we can relate, again, these to orogenic activity. And the 2 main orogenic events are the Svekofenian event, or partly the Svekofenian event, which was old Paleozoic, so it's Paleoproterozoic in age, and a slightly more younger Svekofenian orogeny, and I'll talk a little bit more about those when we come into the detail. Now, the important thing about these major Gneiss regions is that they host big bodies of peridotite. And when I say big bodies, I'm talking about an areal extent of something in the order of tens of kilometers. So these are pretty large bits of peridotite that we find within these Gneisses, not your little tiny blobs. Right, quick bit about ultramafic rocks. Peridotite is an ultramafic rock, and as you can see there, it's mainly olivine, but there's some pyroxenes in there as well. Now, crucially, if we want to call this an ultramafic rock, it's got to have less than 45% SiO2 in its whole rock analysis. Anything above 45% isn't an ultramafic rock. So 45% below, those are ultramafic rocks. And remember, this is SiO2 and the overall chemical analysis. It's not silica. Sorry, it's not quartz, it's SiO2. So anything below 45% is an ultramafic rock. And if the ultramafic rock happens to be composed mainly of olivine, then, as it says there, it's a peridotite. Now, we've got various sorts of peridotite that occur. These definitions I've put down there, they're sort of rigorous, but folks don't always stick to them. But we've got bodies that are peridotite, and they're formed by the accumulation of crystals. So these formed by crystal settling. We would call these cumulate rocks. And the settings where we may find crystals forming are cooling magma bodies. So Wherever you've got a body of cooling magma, we've got the potential to have layered peridotites forming, given the right cooling conditions. And they build up as these accumulations of crystals. We've got another type of occurrence of peridotite called the alpine type, and these are the ophiolitic peridotites. So these are the subcontinental parts of oceanic crust and continental areas that have been caught up in continental collisions, and where we have the oceanic crust and the neighboring continental crust caught up in continental collision, we can find the sections of oceanic crust and attendant underlying mantle incorporated into the continental sections of mountain areas, the Alps, for example. And it was in the Alps where a lot of these early ophiolitic bodies were studied. So that's two types. We've also got this third category. This is the one that we're going to be concentrating on, what we call orogenic peridotites or mantle peridotites. And these are, they're not layered, and we can't really relate them to any apparent ophiolitic genesis. So these just occur as bodies of mantle type peridotite, which we find in orogenic zones. And associated with these, we've got these things called mantle xenoliths. And these are things that are brought up in volcanoes. And again, they come from very deep down into the mantle, way down into the mantle. And we often find, not exclusively, but often find these xenoliths in association with these rocks called kimberlites. And kimberlites themselves are strange rocks. They are, you could call them, well, they sort of ultramafic in a way. They're often very rich in olivine, very rich in pyroxenes, but they've also got strange things in them, like quartz and micas. So they are very, very interesting rocks, and they are comparable with another group of rocks, which we call the lamprophyres. So there's a similarity between the two, and there's an association of a common genetic origin between the two. So let's look at some of these bodies of peridotite. There's a layered peridotite there. Those are layers of olivine. The browny stuff is olivine, and the lighter material is pyroxene. And these are collections of crystals that are formed by crystals settling in a magma chamber. This is the Paleogene Cullin magma chamber on the Isle of Skye, and say those are bodies of various layered crystals. You see those on a larger scale as well. This is also in the Cullin, and if you look in this area here, you can see demarcations, and these are the lines of different of these areas of crystal settling. I think we've got to, yeah, just put the boundaries on for you to see. So this is layering, and these are all olivine rich rocks, and these are all layered on a much larger scale. And this, just point out this footpath where I can find my pointer, which is here it is. This footpath up here, very interesting footpath, because it takes you up past some really olivine and magnetite rich horizons up there, really fascinating to look at. So that's some accumulations of crystals and crystal settling. There's another peridotite. This is what we call the ophiolitic type. This is in South Island, New Zealand, and it's from a place called Mount Dunn. And the reason I put this one in here is because it's the type locality of a rock called dunnite. And as you'll see shortly, dunnite is a type of peridotite, so it's a very important area. But this is a piece of oceanic crust, oceanic lithosphere, that was incorporated into a mountain building event in the Permian, and that's now represented in this South Island, New Zealand. And there we've got that's a bit of a mantle xenolith. You can see the scale on the bottom there. That's 1 centimeter. Some frothy lava. This is basaltic composition lava, but this is all olivine. and this is from the Canaries. So that's a mantle xenolith. Right, we talked about the terminology of these things. We put it on the classic triangular diagram. Don't bother about these big black arrows for the moment. I'll talk about those later on when we get to the appropriate point. So peridotites, we've got mainly olivine. This is olivine up the top end of this triangular diagram. Then we've got orthopyroxene and clinopyroxene. So if we've got any of these in a rock, it is a peridotite. Like I say, I'll talk about these things shortly when we come on to them in a bit more detail. But remember dunite, and that's the type locality that I've just shown you. Right, let's go back to Norway. There's the western Gneiss region. It's sitting there, quite picturesque, a very pretty place. And the area that we're going to be concentrating on is in this area near a place called Stadlandet, which is the peninsula up here. And this is the big body of olivine and dunites in the Almklofdalen region. There's also smaller areas of these peridotites. There's some there, and there's bits dotted around in here with all these other exotic rocks. So that's the area we're going to be looking at, that particularly in the Almklofdalen area in there. Right, so let's move into Almklofdalen in a little bit more detail. Got the scale there, there's a kilometre scale there for you to look at. And we're going to be looking first of all at Gusdal Quarry. That's the first place. And let's see what we can find in Gusdal Quarry. There's Gusdal Quarry. All this is olivine. That's all olivine. It's looking a bit brown because it's all been surface weathered. That's all olivine. And that's Lake Gusdal that connects up to a fjord, a sea loch, and that allows transportation of this material, which is being mined. This is what the quarrying operation is all about. It's all about olivine, and it's used in the steel making business. And it's shipped out, say, from Lake Gusdal down into the fjord and then out to wherever it's needed. We look the other way. That's the main working part of the quarry with the obligatory person for scale. We've also got some vehicles down there that'll give us a scale, and these are the working faces, and this is all olivine. All this here is all nothing, well, almost nothing, but olivine. So you can see this is quite a large extent of olivine. Let's go and look at this a bit more closely. There we go. I'm standing in front of a cliff of olivine. That's all olivine. You possibly pick out some darker bands in this area here. We'll talk about those in a minute. So this is all olivine. It looks slightly, you might expect that mantle xenolith I showed you just now. That was quite nice and green. This is quite a grayish green color, not really what you might expect for olivine. And I'll talk about that in a moment. A lot of this stuff is relatively fine-grained, but there are areas where we get megacrysts of olivine, and there's quite a nice megacryst of olivine there. There's the handle ends for scale. Now, I was talking about these darker areas. There's some there, bits down there, and a little bit there. This is chlorite. This is the mineral chlorite. And because this ultramafic rock has chlorite in it, we would call it a chlorite peridotite. So this is a chlorite peridotite, which is an ultramafic rock, mainly composed of olivine. And there's our olivine megacryst there. Another view of these olivine megacrysts. Very pretty. These are slightly more green, as you will notice. And there we've got some more of this chlorite. The chlorite does occur in discrete veins within this body of rock. And there, this is quite a chlorite-rich area. There's chlorite going up there, chlorite there, and some chlorite over there. Right, okay, what do we know about this body of peridotite? In most of the outcrop or the mined area, it falls into the classification of dunites. So it only contains pyroxenes and olivine. The bit I was showing you just now, that's got chlorite in it, so it's a peridotite. When we analyze it chemically, it is mainly the phosphoritic olivine, the magnesium-rich olivine, and magnesium-rich olivine is phosphorite. It's often called grey olivine because it does tend to have more of a grey colour rather than the bright green of the very iron-rich olivines. So most of this is this magnesium-rich olivine, this phosphoritic olivine. And when we look at the ages of these dunites, or the chlorite peridotites as well, they give us a range of Archean ages. We'll talk about those in a little bit more detail. When we look at the chemistry, the first very interesting thing becomes apparent, because these peridotites are very, very chemically depleted compared to what you could call ordinary peridotites. And they've lost aluminium, they've lost calcium, and they've lost sodium. They've also lost quite a lot of other things, but the main ones, calcium, aluminium, and sodium. So we need to have some means of explaining why these peridotites, dunites, have lost these chemical elements. We'll come on to that shortly. Right, well, that's the Guzdal exposures. We're now going to move on to these exposures down here in Leon. And well, you can look at the key here. It is obvious that we have some garnet peridotites in here as well. So we'll expect to be seeing garnet in here as well. Now, I need to come back to this diagram and do a bit more explaining here. We talked about the original dunite identification with mainly olivine. If we've got orthopyroxene and clinopyroxene as well, then it becomes a peridotite. More terms to come in now. Where we've got some orthopyroxene and clinopyroxene in this area of composition here, that's called Leutzolite, and it's named after Lake Lurtz in Switzerland. So this is what we call Leutzolitic mantle. This is all mantle rock, and this is Leutzolitic mantle. Now, if we allow some partial melting by whatever means to take place in our Leutzolitic mantle, if we extract magmas, melts from our Leutzolitic mantle, the magmas trend in the direction of this big broad arrow here. They go up in that direction, and what we find is that the clinopyroxene becomes taken out with the melt. So the melt is enriched in clinopyroxene. So conversely, the bit that's left behind, the bit of the mantle that hasn't melted, becomes depleted in clinopyroxene, and effectively it becomes enriched in orthopyroxenes. And if any of you have been on my trips to Cyprus, you will no doubt remember me showing you examples of mantle Hartsbergites, that's the name here, that were rich in, or relatively rich in orthopyroxene, but totally lacking in clinopyroxene. So we get Leutzolite mantle rock. We partially melt it, we generate a melt wherein a lot of the clinopyroxene ends up. Originally, we would have called this Leutzolitic mantle fertile. That means it's capable of generating melts. Now, when we've taken a melt out of Leutzolite, it becomes what we call residual. The other term we use is refractory, because it also increases its melting temperature because we've lost lower temperature melting components. So the residual mantle, or the refractory mantle, is what we call Hartsbergite. So whenever I'm talking about Hartsbergite, it is the residual mantle. you'd be hard pressed to get anything, any liquids out of Harzburger. It does happen under very extreme conditions, but you really have to work hard to get melts out of this residual mantle. We don't need these websterite or whorlite, but they're just, as it says there, they're just names for those pyroxene-rich rock types. Right, so let's move on to Lien. This is Lien. This is Helga's Hill Lake, and there was a story about Helga. Sadly, I've forgotten it, so you'll have to make up your own story about Helga, but she had some notoriety here for some reason. But anyway, you look at this. This is classic. This is classic peridotite country with this brown weathering rock. And if we look at the map of the outcrops, this is all the gneiss. These are all the gneisses, and there we've got the gneisses here. And these things are emplaced within the gneisses, and these contacts appear to be mainly tectonic contacts. So the incorporation of these bodies of mantle come about tectonically. And I'll come on to that in more detail later on. It's important to remember that. And this is the area that we're going to be looking at, this area around here. And again, you can notice from the key that we've got garnet peridotites and garnet pyroxenites within there, which we'll look at in a moment. Right, so here we are in a little bit more detail now. Again, there's this rusty brown weathering. Once you've looked at ophiolites across the world, you begin to recognize these colors of any ultramafic rock. Also some slightly different stuff there, which we'll look at in a bit more detail. And so here we go. First thing to notice, well, they've got some colors. You've got brown color there, and you've got less brown color there. The less brown colors are in bands. See some discrete bands. The discrete bands seem to have relatively sharp junctions. It's been folded, and the brown stuff and the bands have been folded contiguously. So it's all been folded together. So obviously the folding happened after whatever happened to form these various layers. Now, this is the particular outcrop. You'll notice I'm not using a hammer for scale. This is a highly protected site here. The rock type is exceedingly pretty. It's exceedingly valued by mineral collectors. And ever since a group of, shall I say, Europeans came along to this locality with a big case of dynamite and blew up most of it, the Norwegian government put all sorts of prohibition orders on it. And I was not allowed to bring my hammer into this area, which is why I'm only using my hand lens as a scale, and quite right too, because these are of worldwide significance in terms of geology. Look at it in a little bit more detail. Again, you can notice the quite sharp bands with these junctions here, quite sharp contacts. Brown material there. You can notice even at this level there are spots within these bands, and those spots are garnets. Look at those in a moment. Now, looking at this contact, you look at there, that's a sharp contact all the way along there. And all these bands within this brown rock all have these sharp contacts. Now, when you look at the grain size of the rock there and the grain size there, there is no difference. There is no chilling. That's going to be important in a moment when we start to think about the genesis of these various rocks. Come into it in a little bit more detail. Now, here are the bands. So you've got bands here, that's a band. There's a sharp contact between the band, this sort of more grayish colored band, and the brown material in the middle. We can look at it here in a bit more detail. That's the contact. This is one of the bands with all its dotted garnets. But if you notice here in this brown bit, there are garnets as well. We'll look at those in a bit more detail in a moment. So that's what we get to look at to start off with. Right, let's start doing some analysis now and see what this all means. Well, for a start, the brown stuff, this is, it's a peridotite. Where there's some garnet, we would call it a garnet peridotite. But there's also areas in here which we will call dunite. So it's only got olivine and well, olivine, mainly olivine with a little bit of pyroxene. We can date this, it has been dated, and it gives us ages of somewhere in the order of 3.5 GA. So that's Archean. We also know that it's come from somewhere in the order of 400 kilometers depth. It might be more, it's more likely to be more, but it's certainly around 400 kilometers depth. And at this point, let's remind ourselves about the deep mantle and what happens deep down in the mantle, where we go from mainly olivine to a point where at about 410 to 650, 670 kilometers depth, we go through something called the mantle transition zone, the MTZ. And as we go down through that increasing depth zone, first of all, the seismic velocities of the mantle change. That's how we originally knew there were interesting things taking place. And at that depth, olivine becomes unstable and it converts into the more stable forms of magnesium silicate, wadsleyite and ringwoodite. So those are the more stable forms in the mantle transition zone. And what we also can recognize is that this material formed part of the Archean subcontinental lithospheric mantle. Now, this was at the time when we were only just beginning to form continental land masses, continental material. We were beginning to generate our suites of TTG rocks, of strontiumites, tonalites and granodiorites, which formed part of that very earliest continental material. And so here we've got bits of the Archean subcontinental lithospheric mantle. Now this is exciting in its own right. But when we look at these chemically, these are very depleted chemically. Again, they've lost those elements that I talked about earlier, the calcium, the sodium, and the aluminium. So let's carry on with this examination. We looked just there at the dunite layer or the peridotite layers. Now let's look at these other bands that we've got here. We've got here part of the, this is the band here that we're looking at there. And then this is the brown stuff in the middle, which we now know is a dunite or a peridotite at least. And the mineralogy of this band here is ophiditic pyroxene and garnet. So it's a pyroxenite because it's mainly pyroxene, and it's got garnet in, so it's a garnet pyroxenite. This bit here, which is relatively poor in, well, almost no pyroxene at all, just olivine, that classic brown weathering characteristic. It's a peridotite, but it's dotted with garnets all over the place, so it's a garnet peridotite. Now we can go a little bit further. There's a little bit of chrome dioxide sitting there just to excite you. When we look at the chemistry of the garnets particularly, they're quite fascinating because these slightly pinkish coloured garnets up here are relatively poor in chromium, whereas these garnets here in the peridotite, these nice purpley garnets, these are pyrope garnets, by the way, these garnets here in the peridotite are this lovely deep colour and they are chromium rich. So something interesting going on here. Let's continue our analysis. When we look at the ages of these garnet pyroxenites, those are the pyroxenite veins, they give us an age of about 1.8 GA. It was a slight spread, but it's around 1.8 GA. Now, if we look at the Dunnites, remember the last ages we've had for these Dunnites, or the rock type with this brown weathering color, we had Archean ages. Well, when we look at these garnet peridotites here, we find a whole age range from 3.5 GA, give or take a bit, to about 1.8 GA. Much greater range. And that's not the only exciting thing, because, as it says at the bottom there, those garnet peridotites are not depleted. They have fertile chemistry. They've got a fertile composition. So let's put this all together. Right, here we've got Gusdal Quarry. It's a peridotite, and in some places it's a dunite, i.e. it's got mainly olivine and almost nothing else, garnet free. Archean ages for the Dunnites, about 3.5. Now, the very depleted chemistry tells us that we've had an extraction event. So this Dunnite here has been involved in the generation of some melt. It has had melts extracted from it, which is why it now has very depleted chemistry. Now let's go on to the Leon outcrops. And first of all, we look at the brown stuff. Again, the garnet-free Dunnite. That again has got Archean ages, about 3.5 GA, give or take. It's very depleted. And it comes from a depth of somewhere between, well, 400 probably. It's probably quite a bit deeper than 400. And what we haven't found out yet, but we are now going to divulge, is that it has had an extraction event which we can date at about 3.1 GA. And we know from the chemistry that what we extracted from this melt was something called a komatiite. These are very exciting rocks. We don't find komatiites in the world anymore because they only formed very early on in the Earth's history. They are, well, they're a bit like lamprifiers and a bit like the kimberlites, sort of, in as much as they got some quite strange chemistry. They are very, very magnesium rich to start with. And that tells us something quite important, because we can generally, rule of thumb, correlate magnesium content of our melts with temperature of melting. And when we've got melts as rich as we have in these komatiites of magnesium, then we can get an idea about at what temperature these formed. And these formed at about 1800 degrees centigrade. That's pretty damn hot to generate melts. And we also know that they were generated at about 350 kilometers depth, because by looking at the barometric indicators within these rocks, they were formed at around 8 gigapascals. That equates to about 350 kilometers depth. So there's quite a few very important things to note about the formation of these melts. Firstly, well, they happened in the mantle. Secondly, they happened at very high temperature. And just to give you a sort of rule of thumb about temperatures, when we look at an average mid-ocean ridge today and look at the temperature at which we form these basaltic oceanic crust magmas, we're talking 1100 to 1200, something of that order. If you stick a thermometer into Hawaii, stick it into one of the magma lakes there, it's about 1100, something of that order. So these komatiite melts were extracted at one hell of a temperature, and we'll talk about that aspect in a little bit more detail later on. Right, it gets a little bit more interesting now, because when we look at the garnet pyroxenites, so we're now looking at these bands again, these we've identified as pyroxenites. Yeah, we've got Proterozoic ages. They've also, I didn't mention it at the time, but they have undergone eclogite facies metamorphism, because the mineralogy that we had there of the omphacitic pyroxene and the garnet, that's eclogite facies mineralogy. And eclogite facies, as you all know, occurs very, very, very deep. And we're talking, yeah, 50, 60, 70, 80, 90, 100, 200 kilometers down into the mantle. Doesn't finish there, though. The garnet peridotites arc into Proterozoic ages. Remember, we have this age range here. And so look, we've got the pyroxenites at 1.8, and we've got these, some of this garnet peridotite at 1.8 as well. And we also know that they are not depleted. Now, those earlier peridotites, those earlier dunites that we looked at from Guzdal and the other stuff we've just looked at Lien, they were depleted. And we know now that they were depleted because they had melts taken out of them. But there's something strange about this bit of peridotite, this bit of garnet peridotite here. And what we believe to be happening is that this pyroxenite was originally a melt. It's a melt channel, or you could call it an igneous dike. That terminology doesn't really fit under these mantle situations, but it's a channel of melt. And we know that it was generated at 1.8 thereabouts GA in the Proterozoic. And this melt percolated through the mantle. So it's a separate body of melt percolating through the mantle at about 1 GA ago. And what it has done, fluids from this melt, and this melt would have sort of been basaltic, if you want a sort of a safe handle to grab hold of, a sort of basaltic. Fluids rich in, well, iron, calcium, aluminium, chromium, sodium, probably some water. All this would have leached from this melt back into the residual, the Harzbergitic mantle, and has refertilized it. So it's replenished all the chemicals that were lost from this bit of mantle when it produced its melts at 3.1 GA have now been replenished. We think it's most likely that the replenishment took place, well, obviously sometime around 1.8 GA or maybe a little bit after. We can't really get a proper age on the refertilization, but it represents metasomatic refertilization of infertile, of residual mantle. And that is very significant. That's very important for, well, for what the mantle does. Right, okay. We've got a journey to go on here of our lump of mantle. Right, let's start off. Where do we start? Well, we start in the Archean. Yeah, we've got that 3.5 GA. Probably, I've put 450 Ks there. There's your mantle transition zone between, I don't know, 420, 430 to 680, something in that order is about the general area of the mantle transition zone. So 3.5 GA, a bit of mantle, possibly from a very, very, very deep mantle upwelling, begins to cool. And as it begins to cool, it sets the atomic clock at 3.5 GA. It then carries on rising up, and it gets to about 3.1 GA. At 3.1 GA, then we start to generate a chematite melt from it. And we continue to rise up. Now, at some point, oh yeah, we've got residual depleted mantle. So what we're left with is now has become depleted. And this is the Guzdal and the ordinary Lien material that we've just looked at. Now, at some point, this material went back down deep into the lower reaches of the mantle, and possibly went down as far as the core mantle boundary. It's difficult to tell that, but we know it's gone back down again. Did it happen there at this point, or did it happen at a slightly different time? We don't know. We haven't got any way of really getting a handle on that, but we know it did go back down at least once. Right, so the next thing at about 1.8 GA, and we are 1.8 GA, we then had this melt channel, or these melts being intruded or percolating through our residual mantle at a depth of around 350 kilometers, possibly higher, maybe even a little bit lower. And this, we believe, caused the refertilization of the mantle. So some of that melt percolated into the residual infertile mantle and refertilized it. And then after 1.8 GA, we continue to rise up in the mantle, and eventually this area of mantle, this separated area of mantle, underplates the Fennoscandian continent, and it becomes part of the subcontinental lithospheric mantle. And then we've now got this lump of mantle sitting under there, but our story has to have that mantle incorporated into the Fennoscandian crust. Now, how on earth did we go from this lump of mantle sitting there underplating the Fennoscandian continent to it being incorporated into the crust? So that's the big question. Underplating of the shield into the tectonic, the incorporated gneissic crust. Well, if you want to insert mantle, bits of mantle, into a lump of crust, it seems likely that we're going to need the two close together for that to happen. And when we look at the process of subduction, there we do have quite a good situation for the juxtaposition of descending crust. All right, most of that descending crust will be oceanic, but as we'll see shortly, you can get continental crust being subducted as well. Doesn't like it, but it does happen, as we'll see in a minute. And as this crust is being subducted, we have the mantle wedge above the subduction zone. That mantle wedge is in close contact with the crust, and so that is a perfect place, most likely place, where we can incorporate our chunks of mantle into our gneissic crust. So let's look at some evidence. When we look at the Peridotites and the Western Gneiss region gneisses, they've got comparable metamorphic ages that span right the way through the Proterozoic. So they've got common metamorphic history. And the ages are coincident with these major tectonothermal events that affected the Fennoscandian shield. I mentioned these earlier, but we now come into them a little bit more deep. We've got the Sphecofenian orogeny around 1750 to 1600, and the Sphecco-Norwegian orogeny around 13 to 950 MA. So we've got the opportunity, the situation, a favorable situation, whereby we can incorporate our bits of underplating mantle into our crust during, well, for our southern region of the Western Gneiss region, it was the Sphecofenian, Sphecco-Norwegian orogeny rather, that was the important one. The Sphecofenian is more noticeable further north. But whether it's the Sphecofenian or the Sphecco-Norwegian, we have the perfect opportunity for those Peridotites to be inserted tectonically into our crust during this phase of orogenic activity. So, did it happen at this point in the Proterozoic? Well, there's sort of conflicting evidence. However, an expert that's studied this in great detail, Simon Cuthbert, believes that the bulk of evidence, when you weigh it all up and look at the detail, it's somewhat against the Proterozoic insertion. And instead, we need to look to the next opportunity for this gneissic crust to be juxtaposed with the mantle. And that didn't happen until the latter stages of the Caledonian orogeny, and in particular, the Scandian event. And so Simon Cuthbert reckons that it's more likely that the insertion took place in the Scandian orogenic event. And this is the envisaged scenario. Well, we've got the continent of Baltica over in that direction to the right. We've got a bit of, well, this is sort of Laurentia, isn't it, really? This whole area here you could regard as Laurentia. We've got our Baltica gneissic basement, this Proterozoic basement. This is the Western Gneiss region here. And we've got our Mantle Peridotites sitting here as part of the subcontinental lithospheric mantle here. And during the oceanic subduction that was taking place here, we have initially, this will be iapetus oceanic crust being subducted, with Baltica on the end of the oceanic crust. Is being subducted underneath Laurentia. Remember, this is the Scandian phase, 450, 440 MA in age. And it was ultimately the collision of Baltica with Laurentia that produced the Scandian event. So initially we have the oceanic crust descending deep down into the mantle, this plane of subduction, but it was towing behind it some unwilling continental crust. And the continental crust, we learn that you don't subduct continental crust. Well, yes, you do, under situations like this. Now, we've got continental crust being dragged down by this heavy oceanic crust that's pulling it down. And at this point, this is when we get the tectonic emplacement of all this mantle material, some of this mantle material, into the Gneiss region as the continental crust is being dragged down. And so this gets dragged down to quite, well, we know that the oceanic crust has gone down to eclogite facies metamorphic regime. So that's, you're at 8-10 gigapascals, or yeah, pretty high, 100 kilometers minimum, something of that order. Now, something interesting, whenever we see subduction and oceanic lithosphere, with advances in modern technology, we can now use something that we call seismic tomography, which is really imaging in high resolution by using seismic wave studies. By using seismic tomography, we can image chunks of oceanic crust that have broken off from their attendant continental crust. These oceanic crust slabs have descended deep down into the mantle intact, or well, they will be resorbing and changing, but they are still identifiable. And we can go down to the core mantle boundary and still image chunks of oceanic crust that has descended to that depth. Right, so back to our situation here. When this oceanic crust anchor breaks off, it then releases this buoyant, remember the density of this continental crust is much lower and it don't want to be down there, it don't want to be dragged down. So as soon as you let go of the anchor, this thing just pops back up again. It's a process we used to call exhumation. But we've now got a term that is becoming more popular called eduction. So we've got subduction going down there. And then when the anchor, if it happens to be a situation where we have an anchor dragging continental crust down, when the anchor breaks, the continental material bounces back up again. And that's what we're now beginning to call eduction. Now, whatever term you want to give it, effectively, it means the stuff has come back up from the deep. Now, if it comes up relatively slowly, remember that all these metamorphic chemical reactions that are taking place are ostensibly reversible, as long as we've maintained closed systems. And so if this material comes back slowly, it will have experienced maybe eclogite fascies metamorphism when it went down, but as it comes up slowly, it can re-equilibrate and go back to where it was originally, amphibolite fascies or something relatively mild. However, if it comes back quickly, we don't get any what we call retrograde metamorphism taking place, and we will have the high pressure assemblages intact. And in the Norway situation, in the Western Gneiss region, we have exactly the rapid exhumation situation where we have not undergone significant retrograde metamorphism. So we can still identify these high pressure fascies materials within this gneissic basement crust. So that's the important bit about the Norway stuff. And so that's effectively our contorted journey of our bit of mantle that started 3.5 GA, 3.5 billion years ago, possibly near the crust mantle boundary. And it's gone back to that crust mantle boundary, possibly at least once again during that cycling. So what? What does it mean? What can it tell us? Well, there's lots of things it can tell us. Firstly, there's mantle circulation. We think we know about mantle circulation. In fact, it ought to be circulating because it's losing heat. But have we got any evidence of it? Well, yeah, we have now, because we can see that some of this mantle rock has actually done exactly that. And we can almost get rates of circulation of mantle. And for this stuff here, we've got values the order of 10 kilometers per million years. And that can be very useful information like that, because when we look at the formation of supercontinents, we change global tectonics. It's what we call lid tectonics. It puts a lid, supercontinent puts a lid on what's going on, and it's related to how the mantle is circulating. So a knowledge of mantle circulation rates can tell us things about when the next supercontinent is going to form. It also tells us that mantle is inhomogeneous. You get discrete areas of mantle that are different to bits next door to it. Maybe that's something we didn't know before, but we've got evidence that that is the case now. And we can also, again, by looking at these tomography studies deep down, we can possibly see where these areas are, because when we look at the core mantle boundary, for start, the core mantle boundary, that's the boundary between the outer core and the mantle, that boundary isn't spherical, and it's got topography. It's got hills and valleys. It's got areas like continents. It's got depressed areas like oceans. And so we've got this inhomogeneity at the core mantle boundary. So maybe it's not unexpected that the mantle itself is inhomogeneous. The other vital thing that we can learn from this is that we talk about extracting melts. And when you begin to learn this, and this is, you learn how you start to make oceanic crust, for example, or how you make volcanoes on Hawaii, for example. The thought must cross your mind, well, if we're keeping to generate all these magmas, are we going to run out of mantle? Well, now we know the answer is No, because we now know that we can refertilize depleted mantle and make it good again so it's ready to take part in more melt generation. And this will continue to happen. Well, as long as we've got a thermal input to the core. The other thing we recognize from this is that when we started out in the Archean, as we were, or even before the Archean, in the Hadean, as we were beginning to get our differentiation of our layers, and we started to form this very early Archean mantle, that's all become recycled. We recycle the mantle round and round and round again. What else do we know? Areas of melt, actual areas of liquid. Well, at those pressures and temperatures, how you define a liquid becomes a little bit sort of tenuous, but there are areas with an increased mobility at extreme depth within the mantle. Again, that can inform us about things like, well, this controversy at the moment, or the debate at the moment between mantle plumes and tectonics. There's lots of information that we can gain from that. Another thing that we can identify from this study is that way back, well, in the Proterozoic at least, that what was happening to the crust was also happening to the mantle as well. And so the coupling between the mantle and the crust was much more active than it is today. Today, the upper part of the mantle exists separate to the crust. But back in the Proterozoic, at least, we know from these studies that it wasn't like that. And finally, it gives us an idea about the temperatures of the Archean mantle at depth. And again, to have actual handles on that quantity, to be able to quantify, is pretty important. So overall, yeah, these bodies of rock look pretty nice, and they're pretty exciting, and they are very nice when you look at the picture behind the words there, because that is all nice. We recognize that, yeah, the study of this is a lot in it. And so it makes you think, are people working on this? Well, the answer is lots of people are working on it still. And there's still a lot that will come out from studies of these exciting mantle rocks. That concludes our trip to Norway. I hope you found the idea of some of its rocks quite amazing. And I'll just leave you with a pleasant view to say goodbye to Norway.